Hello students, we are starting the third module today. In module 2, we were looking at how the instructions were getting executed, and more specifically we looked at how we can execute them in a pipeline fashion. And if you remember the basic components of the computer, we had the control path, data path, memory, input output devices, right? So in the module 2 we were looking at the control path and data path. In this module, the memory system, we are going to look into the memory. Let's dive in. So in the previous module, we saw that an instruction will go through 5 stages: fetch, decode, execute, memory access, and write back. And during the fetch stage, we contact the instruction memory with an address either from the instruction address generator or the um, branch target buffer, right, in case of branch prediction. And what the instruction memory replies is with some bits of information which we interpret as instruction. And during the memory access stage, we contact the data memory with an address. This will be typically from a load instruction or a store instruction, and the data memory replies us with some data that will be placed in some register during the write back stage. Or if it is for the store instruction, the data memory will write the data. So I guess I missed the arrow here. I'll do that. So if you look at the widths of these, the instruction memory address width would typically be 32 bits, and what it replies will also be 32 bits in case of our RISC-V, right, because the instruction width is 32 bits. In case of data memory, we are going to contact it with 32-bit address, and it's going to reply us with either 32 or 64. And in case if we are just trying to load a byte or store a byte, it would be just 8. Half word would be 16, so on and so forth, right? So the widths replied by the instruction memory and data memory are dependent on the ISA, and the widths of addresses to the instruction memory and data memory are predominantly determined by the memory capacity that this particular processor supports, right? Now so far we have been dealing with the instruction memory and data memory more as a black box. We just assume that we give it some address and it replaces with data. So now in this module, we are going to dive into the more implementation details on how it does it, and in in the process across the generations of the processors, right, we are going to look at what all improvements were there in the memory side. So before we dive into what the memory looks like in the current processors, let's pause for a moment and think about what an ideal memory would look like. We expect it to be fast in the sense that it should be as fast as the processor, meaning that uh, when the processor requests for data, either as the fetch stage or the memory access stage, it should not wait for the data. Rather, it should receive it within that one cycle. We also expect the memory to be as large as possible, right? And typically, if you look at even your mobile usage, right, um, by every now and then we would end up, with memory full issues, and we keep deleting. So I looks like what no matter how large the memory is, uh, we end up using it. So typically we would expect a very large memory so that I would not be required to delete any data. It can be any redundant photo or any redundant video or anything, right? And we expect the memory to come at a very low cost, otherwise we will not be able to afford it. So the cost should be as low if not free. Another aspect of an ideal memory that we expect is that when we store something in it, we expect it to be there. We never expect it to be stolen or uh, lost, meaning that it's not retrievable from that device, right? For example, the typical case would be if your hard disk gets corrupted, right? We'll not be able to retrieve the data, something like that. We don't expect that to happen. We want our storage device to be as reliable as possible. We expect the memory to have high bandwidth. Now, the bandwidth might be a totally new term for you, but I'll explain that in simple term. When we are trying to access one data item, whether it is 32 bits or 64 bits or anything like that, let's say it takes X seconds. Now, when we send to the memory multiple requests simultaneously, we don't expect it to take too much time. We still expect it to take a time closer to the same X. Okay, so that's called the bandwidth. If we send one request or 10 requests, we expect the memory to reply us at the uh, with same time for each of the item, right? And we expect the memory to consume less power. So even though we did not look at the power aspects in this course, of late, I should say from past decade and half, the interest in this has been increasing again because our memory usage has been increasing, and we expect the memory to consume as less area as possible, right? And this was primarily because of some reasons, historical reasons. I think I've mentioned this. Uh, I have cited this picture. I think during module zero also, right? Where I mentioned that this was one of the very first hard disk of capacity 5 MB, which was built by IBM. And if you look at the size, it was huge, right? At that point of time, just imagine uh, your your mobile phone right now has 64 GB or 128 GB capacity, and how was that possible, right? We can't afford to have so much effort in terms, not in terms of money, but rather how to carry it, how to use it, right? We want the memory to be as small as possible so that it can be fit in any device. That was not the case because of technology scaling, right? And here in another picture that I've shown you now, we see a micro SD card from Micron Technologies, right? And its capacity is 1 TB. It came out sometime in 2019, right? You see how far we have progressed from a simple 5 MB disk, which was being uh, moved by 5 people, and now we are at a stage to hold 1 TB of capacity of memory device in just with couple of fingers, right? So require less area is more or less assumed or taken granted for. This is not something uh, very pressing right now. And if we look at what we want, right, we want our memory to be fast, large, and it should come cheap, and it should be highly reliable, uh, should consume less power, and all these, some of them are very much conflicting. For example, you want a fast memory and large memory. How does that work, right? If you want a large memory, the circuit will be large no matter what. So accessing a circuit which is large will take more time. So how do we match these conflicting demands? And obviously for a large memory, the power consumption will also be high, and for a larger memory there is also high chance of data getting corrupted also, right? So all these conflicting demands have to be met. Now added to that, the one of the main issue again, a quick recap of what we saw in module 0, which was the memory wall. We observed that the speed at which the processor was scaling and the memory was scaling, there was a huge disparity, right? Effectively, memory was scaling only 50% of what the processor was scaling at. And beyond some point at 2004 or 5 time, we had we moved from single processor to multi-core processors. So till that time, the latency was the only issue. The memory was found to be slower. But beyond that, what happened is we had multiple cores. It means that multiple requests go to the memory at the same time. Because even if you just consider your 8 core processor. So typically, if 8 programs are running, all of them try to use the same memory, right? You don't have 8 different memories in your system, and not only in your system, in anywhere. That's not the case. So both latency and bandwidth are a problem now. So that's what we termed as the memory wall. So the memory wall is more from the performance front, right? What we expect the hardware or the practical aspect that the hardware is facing. And the previous slide, when we were talking about ideal memory, it is expectation from the end user. Now, how do we meet all these conflicting demands and tricky situations? How do we navigate them and come up with a solution? So to understand that, let's look at one of the classic examples that's given as a solution this to this problem, right? Let's say you are sitting in the library. Of course, at this moment you're not in library, you're at home. Let's say you have a quiet environment. Assume that's the library for you, and you are preparing for your exam, right? At any given moment you will be reading one page at a time, and that page would belong to the book you are holding, right? And typically, if you are sitting at a table, you would pick a couple of books which are related to the current subject that you are that you are reading in. Let's say you are preparing for computer architecture course, you will keep the books which are related to architecture nearby, right? And in a typical library, not only architecture books, there will be hundreds or thousands of the books in book racks. Now, what is the observation here? If you assume yourself as the processing core, right? At any given moment, you'll be reading one page at a time, and you'll be flipping pages to and fro in the same book. And if you at any given point of the time, you'll be having few books, related books to nearby, that would come in handy, right, for more examples or more explanations, etc. And even though there are hundreds of books, you will be still focused on these few books. The task that you had at hand is to prepare for the architecture course. The same way, the it was found that the programs that we write also exhibit some similar behavior. Many a times, or most of the time, the programs will be using small amount of data, even though your program is spanning across tens of gigabytes. At any moment, at any given moment, it's going to use only few bytes of data or few megabytes of data, but not gigabytes of data. So this point is called principle of locality. And this principle of locality has two facets to it. The very first one is the observation that when you try to access a data or the location, we tend to uh, access it in the near future, right? This is called temporal locality. And the other aspect is when we try to access a data item, there is a high chance that you are going to access the data item nearby to it. Let's say we access location X, so there is a high chance of accessing x plus 1, x plus 2, x plus 3, or x minus 1, x minus 2, x minus 3. So the nearby locations, that's called the spatial locality. So the principle of locality says at any given moment we only work with small amount of data, and the temporal locality says when we try to when we use the data, there is a high chance that we are going to reuse the data again. And spatial locality says the nearby locations of the data that we have accessed can also be accessed in near future. So whatever I've explained, let's try to look at it with using some examples. So here we have a vector, sorry, an array V, and we have called a function sum vector. Okay, what this function does basically is it adds up all the elements of this vector and returns that added value. Right now, if you look at the accesses of the data in this vector, we are going to access v of 0, move to v of 1, v of 2, v of 3, v of 4, 5, 6, 7, etc. Right? So this comes under temporal locality. Right? When we access v of 0, the very next access for is for v of 1. Let's look at another example. Here we are having a function sum array rows, and the input to this function is a matrix of size m cross n. And what we are doing is we have a nested for loop, and basically what we are adding all the elements of this matrix A, and we return that value at the end of this function. Right now, if you look at the accesses of this matrix A matrix A, right? So first we are going to access 0 0, then 0 1, 0 2, then 1 0, 1 1, 1 2, right? 2 0, 2 1, 2 2, etc. So here I assume that m and n are equal to 3. So the accesses are typically in the horizontal direction, then we switch the row, then again complete that row, and so on and so forth. Right, again we see that there is some notion of temporal locality here. When we access, let's say, a10, the next access was for a11, the nearby locations. Sorry, this is the spatial locality. Apologies for that. The third example is some array, but here we are doing column wise accesses. Right, so for the same 3 cross 3 array, first we are going to access a00, then go to a 10, then a20. After that, we are going to access the second column, and then the third column. If you look at the accesses, it is column wise, then the next column, so on and so forth. Again, we see that there is some notion of spatial locality, but here the if you assume the elements of the matrix are uh, saved in the memory side by side, a uh, a00 and a10 are two spaces apart. Again, a10 and a20 are two spaces apart. So the distance between two axes is called stride. Okay, so here in example 3 the stride is 2, and in example 1 the stride is just 1. Okay, or because after accessing a00 we access a01, then a02, etc, etc. So here we are assuming that the matrix is stored row wise. It means that row 1 will be stored, and immediately row 2, row 3, so on and so forth. Just like the array is stored, uh, all the array elements are stored in a fixed in contiguous locations, right, side by side. So this way of saving a matrix row by row is called row measure format. But in let's say if we are saving column by column, it's a column measure format. For this example, I've just assumed that it is row measure format. And apart from the array A, if we look at the other variables that we are using, I, J, right, this would be the registers, and N and M would be some data in the static memory, right, as part of the static the data segment, the static memory specifically, and the sum would be again part of some register which will be returned or returned to some memory location by the end of this function. Okay, so this is with the data that our program is using. But if we look at the instructions, is there any locality? Let's look at that. Let's say we take the example one, and here we have a for loop. Let's say that for loop is expanded in the assembly to 5 instructions: I1, I2, I3, I4 and I5. After first iteration, again we go back to I1 and go to I2, I3, I4, I5, etc. Right? So here we have both temporal and spatial locality among the instruction fetches. First we fetch I1, then move on to I2, I3, I4, I5. So this is the spatial locality, and again we are going to access I1. So that comes under temporal locality. So in summary, programs repeatedly access the same variables, and this exhibit good temporal locality. A very popular example for the temporal locality is your matrix multiplication, wherein we take one element of array A and multiply it with all the elements of column in B, right? So we are reusing the same element for let's say n number of times. So that comes under temporal locality, right? And then we move on to the next element in A, that comes under spatial locality. So some programs exhibit a straight type of access pattern, but still they come under spatial locality. And if you look at specifically the instructions, they exhibit both temporal and spatial locality. Okay, now what we started off with is a problem statement that we need a memory that is fast, large, comes at low cost, and a few other demands like less power and high bandwidth, etc. And then I switched the topic to locality, saying that no matter how big our program is, it will use only small portion of it at any given moment, and it will tend to reuse the same portion as part of spatial locality or nearby locations as part of temporal locality. Now, how do we link these? Is locality an answer to the first question? If you have already guessed it, yes, locality is the answer. Let's see how we are exploiting the locality. Basically, we are building a hierarchy of memories rather than considering a single memory at any given time, right? So this is the most practical way of achieving fast and large memory for an affordable cost. So typically, the memory hierarchy is visualized as a pyramid. It has multiple levels. So here I am depicting 4 levels. And as you go from top level to the bottom level, the latency of access would increase, the capacity would increase, and the cost would decrease. Okay, this sounds very good in the sense that in the topmost point we are going to store only the currently uh, used data based on locality, right? And then probably the entire program will be stored somewhere at the bottom level. But how to realize it physically? That question was answered by the circuit designers. So you have to thank your electronics friends for that, because they made available to us multiple memory technologies, right? At each of these level, we use a different technology that has characteristics like it is less costly, or it's slower, or its capacity can be higher than the upper level. So let me walk through all the levels one by one. The very first level is the registers, where we store the frequently highly used data. And as you already know, the number of registers are very less, probably 32, 64, etc. Right? And registers are made up of flip-flops or some fast version of SRAM. And the second level is cache. It is completely based on SRAM technology. The third level is the main memory, or the popular usage is RAM, but both cache and main memory are called RAM, right? Okay. So main memory is predominantly built with DRAM technology, and beyond that we have the secondary memory, and this is built with magnetic disk or tape, or magnetic disk is also called hard disk, right? And of late we have switched from hard disk to flash memory. Now, flash memory is similar to what is being used in USBs or micro SD cards, but if you look at it as size or capacity as big as the typical hard disk, it is called solid state drive, right? You can store probably tens of terabyte in it. So each of these memory technology, right? If you look at the access time, the SRAM takes just a fraction of nanosecond to give the data, but DRAM takes tens of nanoseconds. Flash memory takes thousands of nanoseconds, and disk takes nearly a million times longer time, right? But if you look at the cost, SRAM is the costliest. It will take hundreds of dollars for 1 gigabyte of SRAM. But when it comes to the DRAM, it's quite cheaper. It takes just tens of dollars. And flash memory is even further cheaper. And the cheapest is the magnetic disk, just a fraction of a dollar, right? So now if you look at this pyramid, we are able to get a memory which is large, right? Because we can deploy some of the cheaper memories at the lower levels, which is fast because we can deploy some of the faster memories at the top level and get them working because the programs exhibit principle of locality. Of late, there are some new memory technologies also that are being investigated. Some of the popular ones are STT-MRAM, which is spin transfer torque magnetic random access memory, or we have another technology which is PCM, phase change memory. Okay, so these technologies are also used either at cache or memory, main memory or secondary memory. Not only this, the four levels that I have given are not actually four levels. They is much more deeper. In fact, we have multiple levels of cache itself, L1, L2, L3, and within these levels, the L1 is the smallest and closest to the processor pipeline, and L3 is the largest and it is far away from the pipeline, right? And they're all predominantly built with SRAM technology. In main memory also we can have two levels of main memory 1 and 2. Main memory 1 can be with DRAM, and main memory 2 can either be using PCM or STT-MRAM, right? In the secondary memory also we can have multiple levels as store SM1 and SM2. Typically it's called online memory and offline memory. Online memory is something which is quite fast to save the contents of the program, and it's predominantly based with flash storage, and offline memory is your magnetic disk, right? If you have bought your laptop over the past 3 4 years, you can check that there is some small flash based memory which can be something like 100 GB or 125 GB or maybe 256 GB, along with a hard disk that is huge like 2 or 4 TB, right? So this flash acts as a faster storage and the hard disk acts as a slower storage. So the typical memory hierarchy that we find in any of the modern system, right from your mobile phones to the high-end servers, is something like this. So here we have uh, a die short of a 4-core processors, right? 4-core processor, it has 4 cores, core 0 1 2 3. Each of these core has its own L1 cache. L1 cache is split into instruction and data cache, right? And each of the cores has a dedicated L2 cache with it, labeled L2 cache 0, L2 cache 1, L2 cache 2, and L2 cache 3, right? All these L2 caches are again dedicated to each of the cores, and there is a common shared L3 cache. It will be used by all the cores. Further, we have the main memory, which is based with DRAM technology. So we have some DRAM interface with our uh, processor chip, right? And each of these chips on this DIM is called a DRAM device, right? And group of these DRAM devices will be called as a rank, so on and so forth. We are going to look at it. And this DRAM DIM is managed by the DRAM memory controller, which is again on the chip, right? Further, beyond the DRAM, we have the hard disk or flash drive. Okay. Now the registers L1 cache, L2 cache, and L3 cache are on chip, meaning that they lie beside the process or the cores, and DRAM and the secondary storage are off chip because they are outside the chip. That's a common terminology: on chip and off chip. Okay. Now, who moves the data from one level of memory hierarchy to the another level? So it can be either manual or automatic. Let's look at what each of them would mean. In manual management, the programmer needs to explicitly move the data from one level to another level. In automatic, the hardware internally manages the data movement, and the programmer is oblivious of this. Manual was how the evolution started with, right? But it was found to be too painful. Imagine you writing a matrix program saying that if the matrix size is beyond let's say 32 cross 32, then move then we need to use a larger main memory or something like that. We don't do that at all. We don't even bother uh, how big is our RAM when we write our program, isn't it? So we have moved from manual quite some time back, but it is still preferred in some of the embedded processes wherein instead of cache we have something called as scratchpad. Again, it is based on SRAM technology. And the most recent one is the GPUs, where we have something called shared memory. The programmer, if you are familiar with the GPU programming, we need to explicitly say where the data is stored, right? And when to get the data from that shared memory to the GPU cache. Okay. But in automatic, the programmer's life is easy. All you will be doing is focusing on the algorithm and making it as efficient as possible, and try to run it as fast as possible, etc. Right? Uh, any average programmer does not think about what hardware he's going to run his program on. But we are not an average programmer, right? Now we have an understanding of the underlying hardware. So think about how your program can run faster from now onwards. Any program that you write, keep keep the underlying hardware in mind and see how you can make it run faster. For example, just to correlate with what you know, try to avoid the control instructions as much as possible, right? If you have a way to minimize it, minimize. Otherwise, you might end up with a lot of stalls in your program. In the same way, in this module, you will learn that having an understanding of the underlying memory hierarchy will help you to write a program that will run faster. So the block level view of the modern memory hierarchy is we have a register file, and typically it can have a size of 64 of size a word each, and it takes a fraction of nanosecond to access, right? Below that we have the L1 cache. Typically its size is 32 kilobyte and it will take a few tens of nanoseconds, and the data between the register file and L1 cache will be moved to and fro by the compiler, basically with your load and store instructions. Beyond L1 cache we have L2 cache and L3 cache, right? All the data movement between L1, L2, L3 is managed by the hardware, right? And beyond the caches, we have what's called main memory, and the to and fro from the caches to the main memory is again a mix of hardware and software. But the uh, movement of data from the main memory to the storage, or a easier or more relatable term from in context of operating systems, is swap disk, right? The data moment is managed by the operating system itself by employing what's called as demand paging. So we are going to look at how each a cache works, how a main memory works, how a solid state drive works, and how the data is moved across in this module. Okay. And side point, as we move from the registers to the disk, right? There is abstraction of memory, increasing level of abstraction. If we are looking at registers and their usage, you will be working at assembly level. But if you are uh, working at the programmer level, you don't worry about anything else than having a good enough or large enough disk, right? And the notion of memory hierarchy is so pervasive that you will find it everywhere in many of the current day deployments, right? Let's look at them. We saw the registers. It is managed by the compiler, and we also have what's called TLB, translation look aside buffer. We are going to look at what TLB is also. It is managed by the hardware MMU. MMU stands for memory management unit. Then we have L1 cache, L2 cache, L3 cache, and the hardware manages the to and fro of data. And if you look at the sizes of the granularity of data at the CPU registers, we deal with 4 to 8 bytes of data at a time, which is called a word. And we will come to TLB a little later. In L1, L2, L3, we deal with sizes 64 bytes at a time, and beyond that, we have what's called virtual memory, and here we are going to deal with sizes of 4 kilobytes, right? And main memory or DRAM based memory is what is used by the virtual memory, and it is managed by both hardware and software. Beyond that, we have what's called buffer cache. It stores, or it being the operating system stores parts of some of the files which are frequently used in and place them in the main memory itself. After the buffer cache, we have what's called disk cache, and disk cache is within the hard disk, right? And the hard disk controller uh, manages the to and fro movement of the data in it. We have something called network cache. Again, some parts of the files are stored on the local disk so that you'll be able to connect to the network easily, right, without setting it up every time, etc., right? And one other relatable example is your browser itself has a cache, right? It will cache few of the recently visited web pages, recently or frequently visited web pages, and that data is stored in your local hard disk. And the web browser application itself will manage what needs to be cached and what needs to be discarded. And we also have a web cache which is similar to the browser cache, but in server kind of environment, where the server will uh, the web server where it's being hosted, right, will keep a track of the recently or frequently used pages, and it keeps them closer to it, so that whenever a new request comes, it will load fast. So the notion of memory hierarchy is quite widely used, and it's everywhere. So with that, I'll pause this lecture. What we saw in this lecture is the notion of ideal memory, what is expected, right, and how uh, by intuition based on how a program would work, right, the concept of locality has been proposed, and how that helped us to achieve the ideal or closer to ideal memory in our day-to-day uh, computing equipment, right? With that, I'll pause this lecture. Thank you.